Our first changemaker of the evening is Hoda Ahmed, a PhD student in the Department of Mining and Material Engineering, working under the supervision of Professor Jinhyuk. With Hoda, let's take the journey to find out how salt can help us create sustainable batteries.
There are three big problems with the battery you see in this car. It doesn't have enough range. So if you want to drive faster than Quebec City, you might wish you had a gas car. Also, it's really expensive. Not everyone can afford it. And I believe that most of you guys know that this car is not green. Yes, because the battery in this car is not green. It's full of toxic chemicals. So today, in the next 10 minutes, I'm going to teach you how with my research, I try to solve most of these issues. But I think now everybody curious about lithium-ion batteries. Let me first explain to you what is lithium-ion battery. Lithium-ion battery consists of two main electrodes, anode and cathode. Lithium ions move back and forth between these two electrodes through the electrolyte. When we initially build lithium-ion battery, we build it in a dead form or in a discharged form. Why? Because all the lithium ions are in the cathode structure. Once we started charging it, we forced lithium ions and the electrons to move from cathode to anode. Now we have our battery fully charged. Once we started driving our car or using our phones, lithium ions and electrons will spontaneously move back to their original structure, which is the cathode part. So this lithium ion movement back and forth between cathode and anode determine how much energy you can store in your battery. As you can see, there are several components in the lithium ion battery. Among all these components, I choose to work in cathode material. Why? Because the cathode material is the most expensive and heaviest component in the battery, which means it is the component that determine or that has the most influence on the battery cost and energy density. So there are several kinds of this cathode material, most of them made of cobalt and nickel. Let me show you one of the most commercialized cathode material. This cathode material has layered structure. And for simplicity, I'm just giving you here a simple example, which is lithium cobalt oxide. In the layered material, lithium and transition metal, which is cobalt here in our case, are arranged in alternating layers, which means we have lithium, cobalt, and so on. With this layered material, we can get around 600 watt-hour per kilogram energy density. And watt-hour per kilogram is how we measure the energy density. And this material will be our reference point for today's presentation, which means I will compare my material performance later with this material. So now let me introduce to you the material that I choose to work with. This material, or the material that I choose to work with, has more lithium in the structure. Also, it can be made of manganese instead of cobalt. And unlike the layered material, this material, or the lithium ion and manganese in this material, can be made of or it's randomly distributed in the structure, as you can see in this image. So let me tell you the name of this material. This material called lithium-rich disorder rock salt cathode material. I know the name is too long, but the good news is you can just call it DRX. So the question now is, why I choose to work with this specific cathode material? Why I choose to work with DRX? Simply because this material, or with this material, we can get around 1,000 watt-hour per kilogram energy density, which is very high comparing to the commercialized one. You might wonder, why, if this material is very good and can get this high energy density, why it's not in our battery yet? Simply because this high energy density doesn't last forever. It declines so quickly, as you can see with the red line. So in my PhD, I'm trying to solve this issue. I'm trying to make this red line as flat as possible. Or you can say that I'm trying to make the energy density of the DRX material as stable as possible so we can take advantage of this promising material. Let me explain to you how did I do that. First, I tried to understand why this material or why the energy density of this material declined quickly. I looked into the literature and I found that the main issue with this material is the synthesis method that people use to make it. When people try to make DRX, usually they mix solid precursor. And because the reaction is between solid-solid, it needs high temperature like 1000 C and long time like 12 hours in order to be synthesized. And because of this high temperature and long synthesis time, this led to a very large particle formation. The issue with this large particle is that it will take forever to extract lithium ions out of this structure, especially the one in the bulk. People solve this issue by a simple mean. They just crush this large particle into smaller ones. But as you can see, this small particle, most of them has non-uniform morphology. And there is a big issue with this non-uniform morphology nanoparticles. The issue with this particle is that as long as we use it to make the electrode film that we use to make the battery, this non-uniform morphology particle tend to cluster or agglomerate in a specific region of the electrode film. So now we have non-uniform particle distribution in the electrode film. And as you know that when we charge and discharge battery, we extract lithium in and out of the cathode structure. And this will lead to volume change. And because of the non-uniform particle distribution in the electrode film, this will lead to non-uniform volume expansion and contraction during discharging and charging of the battery. And this non-uniform volume change across the electrode film led to the cracks formation. So now we kind of understand what is the reason behind this fast energy loss of the DRX material. Simply, it is the particle size and morphology. So we thought, what if we can solve this issue? What if we can just make the particle as small as possible from the beginning with a uniform morphology? And we did so. Let me teach you, or let me tell you, how did I do that? When we looked into the literature, we found an interesting synthesis method. This method called molten salt synthesis. People usually use this method to synthesize a very large single crystal. We modified this method to make it able to synthesize a very small single crystal. And this happened by applying two simple steps. Let me explain these steps to you. In the beginning, before we start, we just mixed the solid precursor with a salt, like table salt. And we will understand soon what is the function of the salt in this process. So after mixing the solid precursor with the salt, we heat the mixture slightly above the melting point of the salt. So now we are above the melting point of the salt. The salt will melt and act as a liquid medium. Now the solid precursor, you remember the solid precursor, now it will start dissolving in this molten salt. So we transform the solid-solid reaction to liquid-liquid reaction. Everything now is ions. And this will speed up the reaction. Therefore, we were able to reduce the reaction synthesis temperature from 1000 C to 800 C. Also, we were able to reduce the reaction time from 12 hours to 1 minute. So after 1 minute, we immediately stop the reaction by cooling down the furnace. After this first step, we got like our pure DRX product. But remember, we still have the salt. So now the salt is solidified surrounding each particle. Imagine we have a spherical particle surrounded with a membrane or a solidified salt. But when we checked the image of this particle, we found that there is some non-uniform distribution of the element. And it's obvious because we already used like low synthesis temperature and time. That's why we applied a second heating step. In this step, we heat the mixture or the product of the first step, the one with the single particle surrounded with the solidified salt, but this time we heat it below the melting point of the salt. Why? Because of two reasons. If we heat the mixture in the second step above the melting point of the salt, that means the salt will melt and the reaction will proceed. So the particle will get bigger and bigger, and we want to avoid this. That's why we heat the mixture below the melting point of the salt. And the second reason is that because now we have the single particle surrounded with the solidified salt, we want to take advantage of this solidified salt. Therefore, this solidified salt will act as a physical barrier, which will prevent any further contact between the particle, and this will prevent any further particle growth. So now, by applying these two steps, we obtained, or we were able to transfer all this non-uniform particle to a uniform particle, as you can see in this image. So now we have a nanoparticle or a single crystal nanoparticle. Now we have the material ready to go. But remember, we still have the salt. You remember I told you we have the single particle surrounded with a solidified salt? So now we have the particle still surrounded with the solidified salt. We cannot use this in our battery. So we need first to remove the salt. We did simply by washing the material in water. So after this washing step, now we have our single crystal nanoparticle ready to go. Now we really can use the material. But anyone curious before I move on to see the real image of this particle? Okay, here's our beautiful manganese-DRX single crystal particle with a particle size less than 200 nanometer. And as Professor Jeff said, it looks like a marshmallow. But we are not going to eat it. We will just use it to make a good battery. So indeed, and with this nice looking morphology manganese-DRX material, we were confident that we will get a very nice performance. Indeed, when we used this particle to make the electrode film, we achieved a nice particle distribution, as you can see in the electrode film, unlike the one that used the crushed particle. With this nice particle distribution, we made the battery, or we built the battery, and we got this performance. Unfortunately, the performance was terrible. It was a huge shock for us. As you can see, the performance is like the blue line one. So we started thinking, what did we do wrong? We revised every single step in our method. Finally, we figured it out. Do you remember when I told you that we need to wash the material to remove the salt? That's when the problem happened. We didn't just only remove the salt, we also removed the lithium from the structure. So now we don't have lithium in the structure. That's why we don't have energy. We started thinking again. How can we solve this problem? We thought we need first to understand why lithium left the structure in the first place. And we understood this. Let me explain to you. Lithium left the structure because the lithium concentration in the structure is very much higher than lithium concentration in water. Water doesn't have any lithium. Therefore, this made like a concentration gradient. Lithium concentration in the structure is higher, so lithium just jumped into water to reach to the equilibrium. And this helped us to solve the problem. We thought that, what if we can just reverse this process? And indeed, instead of applying a second step and washing the material in pure water, what we did is that we washed the material again, but this time in a highly concentrated lithium hydroxide solution. So we washed the material with a highly concentrated lithium solution in order to let lithium leave the solution and jump back into the structure. And this is what happened. And when we test the performance, or when we test the material, we found that indeed we got our lithium back. So now we have our marshmallow particles with our lithium back in the structure, the material is ready to go. Now let me show you the performance of the material. Oh, it's not this one. This was the terrible one. This is the real performance. As you can see with the blue line, with our synthesis method, we were able to obtain a stable 600 watt-hour per kilogram. It's still not 1,000 watt-hour per kilogram, but at least our material is comparable to the commercialized material or the layered material that has been extensively studied for decades. Also, a good news, my colleagues and I trying to make the particle even smaller and trying to improve the lithium diffusion in the DRX material in order to be able to reach it to a stable 1,000 watt-hour per kilogram. So far, I was talking about the energy density or the range. And I told you that we are working to make a stable 1,000 watt-hour per kilogram energy density. What about the cost and environmental impact? I didn't talk about it, right? Actually, I did. Do you remember when I told you that my material, the cathode material that I'm using, can be made of manganese instead of cobalt? That's when I talked about the range and environmental impact. Because cobalt is 14 times more expensive than manganese. And it's not only about the price. Cobalt mining is linked to unethical practices and environmental harm, while manganese is more safer option and cleaner option. So by using manganese, we are not just turning our lithium, or we are not just making our lithium-ion batteries cheaper, but we are making it more cleaner and more sustainable. And this is the best option for our future. Thank you.